Okay, AP Physics C, are you ready? Just a couple things on two-dimensional motion to help you with these problems, a little more advanced problems. So, um, my computer is dead and I don't have the packet here at home. So I'm gonna look at one very similar to that number 3 on the worksheet, where we have something that's moving and accelerating, right, in one direction, but then another force comes along and starts to blow it off its track with an acceleration this way. So kind of think of like drawing a motion map of it, where let's say we have something that's kind of speeding up this way, right? Straight line motion. Let's just say its acceleration is, we'll say AX is positive 2 meters per second squared. All right, let's say V naught X is 0. And let's make it 1, 2, 3, 4 seconds of motion. T is 4 seconds. All right, but now let's say a gust of wind comes along, right? And it starts accelerating it vertically as it moves. But so I think about the component of the velocity, right, increasing this way as well, but maybe at a lower rate. So now the actual motion of this object would actually look like this, right? This is what it looks like in the x direction. In the y direction, right, it's getting faster, it's getting faster, it's getting faster in the y direction up this way. So overall, I have a path that looks kind of like that, right? So I have to kind of think about drawing this a little bit differently. All right. I got a little too wild with my arrows here. Maybe make it increase at a lower rate in the y direction. So here's the initial path, but now we also have velocity in each direction, right? And the resultant would be tangent to this curve. It'd be the resultant of these vectors I drew. So let's say AY equals positive 0.25 meters per second squared. V naught Y equals 0. And still the time equals 4 seconds. So ultimately would want to figure out here, okay, in those 4 seconds, how far does it displace itself to the right and how far does it displace itself that way? So it's no different than what we've been doing. We break it into x and y direction, but what's different now is that we can't just take for granted that its acceleration in the x direction is 0 and its acceleration in the y direction is positive 9.8. This could be a sailboat. This could be a boat going in water that's also moving this way. This could be like a river where the water's flowing this way and the boat's trying to cross, but it's going that way. I don't know. This could be air, something moving through a fluid that's moving. Anyway, something that has two perpendicular jets. So when you travel in space, you would have a jet pushing you forward and jet pushing you this way, and that would give you this curved path, right? So if we go ahead and figure out delta x and delta y, so delta x equals 1/2 of 2 times 4 squared plus v naught t, which is 0, so 16. Delta x would be positive 16 meters. Delta y 1/2 of 0.25 times 4 squared, so 16. Quarter of 16 is 4. Half of 4 is 2, so delta y would be plus 2 meters. So we have two components to the acceleration, and we still keep track of them separately. If we want to find the resultant displacement, right, which, we need a variable for the resultant displacement, right? So sometimes what we'll say is delta r, the overall displacement, where r is like, r would be a vector drawn from the first point, right? This would be the r vector, the position vector, r vector. And it is worthwhile to think about making these vector quantities at this point. right? So we can keep, it's the displacement in the x direction, it's displacement in the y direction. Really thinking of these as vectors. We add that little arrow over the x and the y, and that turns it into what we call a vector quantity. There'll be a little more on this later on, but the r vector, let me draw it in a different color. The r vector, I should say the delta r vector would be the displacement vector. That'd be the vector from where it started straight to where it finished. Right? That would be the displacement vector. Its position would be, specific x and y coordinate, which makes sense written in a little different notation that we'll find out later on. Now, really, I want the magnitude of that vector, the angle I'd have to figure out. So the magnitude of the r vector is square root of 16 squared plus 2 squared, which, as usual, I don't have a calculator down here. I gotta get set up better back down here for these videos. If I then wanted to figure out the angle it's at theta, it's the tan inverse. Theta equals the tan inverse opposite over adjacent of the y over x, which would be 2 over 16, and you get the angle that way. So I'd have to go about that. Really, the whole point here is you could have any wacky, crazy acceleration, right, in either direction, and you'd have to figure it out. Now, keeping track of things, I could make it a function as well. I could say, okay, you know what? The velocity in the x direction is 3t plus 9. The velocity in the y direction is simply 10. And this would give you units of meters per second, okay? So that means the acceleration of this one is the derivative of velocity. So it would be 3 meters per second squared. This would have to have units of meters per second. This would be meters per second. Acceleration in the y direction would be 0, right? Because this is a flat function, 0 acceleration. I could ask you the displacement over each direction, right? I can ask you for the magnitude of the resultant acceleration. I could ask you for the magnitude of the resultant velocity at specific times, right? We could figure that out. And that's all Pythagorean's theorem, right? So I would have the velocity here is changing in each direction. But again, the whole point is it's really no different than what we've been doing. You just have to keep track of the x direction and the y direction simultaneously, separately, and then recombine them together with things like, well, the velocity, the magnitude of the velocity is equal to the square root of the components squared. The magnitude of the acceleration is equal to the square root of the components, ax, squared. All right. Now, displacement is the weird one, right? Vx, we use subscripts to notate the other directions. With the displacement magnitude that we like to use the delta r, and then we wouldn't say rx and ry, we would just say x squared plus y squared, right? So that's a little different the way we notate position and displacement, which, is just kind of the way we do it. So hopefully that'll help you figure out that number 3. Kind of also simultaneously, it's a little bit of an introduction to the next worksheet, which we'll get going on. Just wanted to get something out there quick so you could wrap up that worksheet 1 and maybe think about we'll be starting probably worksheet 2 next week. All right, so have a good one. Talk to you later.